All right, hello and surprise. We got right to the point at the end of class today talking about the halting problem, but we didn't actually do it, and we have no time on Friday, so we are doing it now. Let's go. I think I can do this in like 15 minutes or less. Because we already set up the big picture, which is we have Turing machines which capture the intuitive notion of what it means for a task to be computable, and every single thing that we think of as being doable by an algorithm can be done with a Turing machine. But we recognize that there are only a countable number of possible Turing machines. So if every computable function has a Turing machine associated with it, and there are only a countable number of Turing machines, there are unfortunately an uncountable number of functions. And so some things just cannot be done via algorithm. The most famous thing that just cannot be done is solving the halting problem. Okay, so I said this already today in class. What we want is a machine, a Turing machine, H, which does the following. Given another program, or I'll think of it as another Turing machine, or another Turing machine, it determines whether that program will halt when fed a particular input. Okay, so to be a little bit more precise, suppose I have a Turing machine, big M, and the example we did in class was a machine which just adds 1. We can, via this thing called Gödel numbering, convert that machine into a sequence of quadruples, and by sticking to a particular syntax, we can actually reduce it down to a sequence of doubles, which tells you exactly what to do in each state when encountering each possible character on the input tape, what to do. And that string can be converted via a coding system into a long sequence of numbers. And those sequence of numbers can be placed in the powers of the primes. And this is in fact the number little m from class. So to each Turing machine big M is associated a code number, a Gödel number, little m. And n, little n, is just some number that we wish to plug into machine big M. And the big question is, what happens when we plug number little n into machine big M? Does it halt or does it not halt? And of course, I think I said this in class already, but just to reiterate, I can't simply run machine M with input little n and wait, because I never know how long to wait. I don't know whether the computation is stuck and will never end, or whether it's just taking a really, really long time. And so built into the definition of an algorithm is that it has to eventually stop. If I knew for sure that machine M would halt when given input little n, then I could just let it run and just wait and wait, and it would eventually halt. But it may never halt. Okay, so what I want is this machine H. And here's what this machine H does. It takes 2 numbers as inputs. So it is a function from a pair of numbers to another number, you could say. And what it does is it answers the question definitively: does the machine which with Gödel number little m, that is big M, does the machine with this Gödel number, when fed this number as input, halt or not? And like as I was kind of just trying to say, but let me repeat it, built into the definition of I have a machine that does a certain task is that this machine must halt. So this machine H, if it exists, I can run it and it will tell me, I don't know how long it's going to take, but it will tell me for sure whether machine big M will halt when fed input little m. Okay, and the theorem is that the halting problem is unsolvable. And to be a little bit more precise, when people say the halting problem is unsolvable, the halting problem, sort of generally, is the problem of determining whether a machine will halt on a given input. But when I say the halting problem is unsolvable, what I mean is that there is no algorithm which will do what the halting problem sets out to do. And more specifically, there cannot exist a Turing machine that solves the halting problem. And if you believe, as everyone does, that the very notion of effectively computable is captured formally by the Turing machine concept, then if there is no Turing machine that can solve the halting problem, then in some sense the halting problem just can't be done. There can be no algorithm which does it. Okay, getting to the details of the proof now. Suppose that we could solve the halting problem with a Turing machine. So I'm just going to assume that we have this machine H, and here's what this machine H does. You feed it two numbers, little m, the Gödel number of a Turing machine, and little n, a number. And what this halting machine does somehow is tells you whether this machine big M, when run with input n, halts or not. And if m does halt on input little n, then this machine will output 1. And it's going to output 0 otherwise. Okay, and otherwise captures a lot of cases. For example, these Gödel numbers, these code numbers, m, for these machines are like these huge powers of primes, right? But the vast majority of numbers are not Gödel numbers of valid Turing machines. For example, if I just set m to be like, I don't know, 2 to the 8, well, actually it's hard to come up with an example on the spot. But if you, I think the way I did it, the first number has to be L or 1 or 0 or something like that. So, okay, the technical details aren't important, but if I just gave you 2 to the 8th, 3 to the 8th, just trust me that when you decode this, it's not going to be a Turing machine at all. It's just going to be a bunch of garbage. So that's an example in which otherwise is relevant. So this halting problem will output 0 if either this machine, this code number m is not the code number of a Turing machine at all, or if it is the code number of a Turing machine, but when this machine is fed input n, it goes on some kind of infinite loop and gets like stuck. Okay, so suppose I have such a machine. Why is it impossible? Why is this impossible? Okay, let's just do the proof right now. Well, what we do is we make a new machine G. And this new machine G takes a single input. G is fed some number V. And what V is hopefully the code number of a Turing machine. So V itself is one of these long numbers of powers of primes, which if decoded gives you the directions of a Turing machine. And now what we're going to do is, this machine G, the first thing this machine G does is it has access to this halting machine that we're assuming temporarily exists. And what G does is to run this halting machine with the V sort of run on itself. Okay. In other words, V is a Gödel number of a Turing machine, but at the same time, V is just a number. And I'm now using V in both ways. I'm basically saying, yo, plug into the machine which V codes the code number of itself. There's some sort of self-reference going on here in a kind of a sense. It would be like if you had some very, very long Java program which took a single input, and the single input to that Java program came in the form of a number. And if you took that entire Java program and you converted every character of your Java program into ASCII, and then you placed the ASCII code for every single character of your Java program up into the powers of primes, what you would get is a code number, and that code number itself would represent your entire Java program. And then you would run that Java program using that number as the input, and you would sort of see what happens. Okay, well, let's just say what actually will happen. If we know, because we are assuming that this halting machine works, we know that if HVV outputs 0, oh no, sorry. What I'm doing is I'm now I'm in the process of defining what the G function should do based on what this H machine does. Okay, so you run this on itself. This is allowed because on the assumption I have this H machine. And if HVV outputs 0, then G should halt. G should halt. I'm defining what the G machine does. And if HVV, H of VV outputs 1, then go on an infinite loop. G should go on an infinite loop. Should, I'll just say loop. Okay, so in other words, we have created this machine G. And here's what this machine G does. Just to put it in words. G halts. When does G halt? G halts under this case. That's how we defined it. G halts on input V if the machine coded as V, the machine coded as little v, doesn't halt when fed V as input. Doesn't halt when fed V as input. Because, and this is getting a little bit complicated, but remember, H answers the question. Maybe I should put it up here if it's possibly off screen. Because what does HMN do? It outputs 1 if it halts, and it outputs 0 if it doesn't halt. Doesn't halt. And so, just make sure I'm in frame. Yeah, sure. Oh, it's still kind of in frame. It's crap video. So what G does is G will halt, as it says right here, only if HVV outputs 0. And under what conditions will HVV output 0? Well, HVV will output 0 if the H machine, if the V machine, when run on V, doesn't halt. That's just the definition of H. And G doesn't halt. Doesn't halt on input V. On input V, if the machine coded as V does halt when fed V as input. Okay, so on the assumption that I have this halting machine, I can create this G machine. And now here's where it gets weird. This G, this turn machine G, also has a code number. So let little g be the code number or the girdle number of machine G. Okay, and the question is, what is going to happen when we run machine G on input G? Okay, well, let's do it. What is going to happen? Well, let's follow the definition. What does how was machine big G constructed? Well, it takes a particular input, and it then calls up the halting machine, and it runs the halting machine GG. And then, as we can see right above, this is the definition of G. If HGG outputs 0, then it halts. Then it halts. And if HGG outputs 1, it doesn't halt. Or it loops. Okay, but now both options lead to a contradiction. Suppose that HGG, so case one, suppose that HGG outputs 0. Maybe we'll just talk this out instead of writing it. Suppose, because I've run out of board space. So the two options are that HGG outputs 0 and that HGG outputs 1. And I'm going to show that both are impossible. Okay. Well, if HGG outputs 0, then, being very careful now, by the definition of G, if HGG outputs 0, then by the definition of G, we constructed this machine G to if HGG outputs 0, it should halt. So by definition of G, by the construction of this G machine then, G should halt on input G. But by the definition of H, by the definition of the H machine, what does it mean if the H machine outputs 0? Well, it means that G should not halt. G should not halt on input G. There's a conflict here, right? The very notion of what it means for HGG to output 0 is that, by the definition of H, that G should not halt on G. That's what this halting machine does for us. But by the definition of G, we constructed the G machine to output 0 in the case that HGG, or to halt on the case that HGG outputs 0. This is a contradiction. So it can't be true that HGG outputs 0. Well, what if HGG outputs 1? Well then, again, by the definition of G, if HGG outputs 1, then by the definition of G, G does not halt. Then G does not halt on input G. That's how we constructed the G machine. But by the definition of H, if HGG outputs 1, then G does halt on input G. Contradiction. So somehow the halting machine can't answer the question of what happens when you run this machine G on its own Gödel number. And regardless of what this H machine does, we have a contradiction. And so our only conclusion with this contradiction, this is kind of a diagonalization on all Turing machines, is really what this is, with an extra kind of step to convert this binary function into a unary function. And what we've shown is that this just doesn't work. So there somehow cannot be such a machine G. But the only assumption that went into the building of this machine G is that we had such a machine H. And so we cannot have such a machine H. This is a tangible and practical example of a function that is just not computable. And this is kind of the tip of the iceberg of a huge number of other problems which can be shown, once you formally adopt this notion of a Turing machine, it can be shown to just be not doable. And the biggest one of all, though I'm presenting them historically backwards, is Gödel's incompleteness theorem. That was historically actually the first result that said you can't do stuff. And this came a little bit later. But we are going to use the halting problem to prove Gödel's incompleteness theorem, because the halting problem is just provable in like 10 or 15 minutes like this quite cleanly. All right, I hope that made sense. I will see you guys in class on Friday. Bye.